Okay, welcome back. Let me ask first of all whether you all want the lights more on or is this good? Okay. Okay, so just a very, very quick review of what we've done the last time. We were looking at I just want to highlight a few things before we go on because there's no it's never a bad thing to revise some things. Basically, you have to keep track of three colors, and this seems to be helping the class. So these are the three things you have to keep straight. Right? They are all proportions, but they are all different. First of all, we have the status quo or hypothesized value of the proportion. That one we color blue. That's the one that you hypothesize about. You don't actually know what it is, but you make a claim about it. So, for example, if you say your friend is guessing on a true false test, that is tantamount to saying that pi is 1/2. And that would be what the blue color represents. Then the red number in red here is the observed proportion that you actually saw when your friend did the true false test or whatever it was. Now, can anyone tell me what's the symbol for this proportion? The one that you see and you observe from your sample? Yeah, good. Not pi. Pi is this one. And then the last number was the one which is in purple. This is a fraction of cases. How many simulations that you made gave you something as or more extreme than what you saw? I think this is the one that's the most confusing to students. This number is also a proportion, it's also a fraction, but they're all different. This is how many simulations were there that you made that were as or more extreme than what you saw. This number is what we call it. I know the computer puts it in red, but we are going to make it purple to distinguish. Does anyone remember what this number is called? This one, right? What is this number called? The fraction that is as or more, the fraction of simulations that are as or more extreme than what you saw. What is this number called? We introduced this the last time. This number is pi, the blue one's pi, the red one's p hat. What is this fraction that is as or more extreme than what you saw? What is it called? See, it is hard. It is confusing, but if you really keep it straight, there are three numbers, three colors, all start with P. Pi starts with a P. Proportion, the observed proportion, P hat starts with a P. P value starts with a P. They're all starting with P. They're all proportions, but they're all different. All right, so you have to keep these things straight. So the fact that this is the P value tells you, it gives you a judgment of how likely you were to see things like this if what you say is true. You say, you say that your friend is guessing on the true false test or whatever. If you guess on a true false test, most of the time, this is what happens. But your friend comes and gets a score way out here. Now, in this case, you never see a score as extreme as that when you guess on a true false test. That is why the p-value tells you there were no cases like that. The p-value is an evaluation of how likely you are to see the thing you actually observe. These are three ideas you have to think about. I'll say it again. The blue number, the blue proportion, is what you hypothesize. That's why we put it as HO. It's what you hypothesize about the process if your friend is guessing, if the dolphin is guessing, if the dog is guessing, if you are guessing. It's the middle one, right? But I actually did the study. So you can actually collect data. That's colored red. That's what you actually saw. So your friend's score on the true false test could be whatever. Right? Then the next task is, okay, is there a special score or not? When you guess, Do you get things like that a whole lot of time? That's the logic of what's going on. So you make the computer generate many, many true false tests under the blue assumptions. These are typically what will happen when you generate under the blue. Most of the things are in the middle, where you said the middle was. And then you draw the red line here to compare your friend's score to what normally happens when you guess on a true false test. And if there's not many cases like that, the p-value is small, then we say that we say that there's support for the alternative. Your friend is smart. You can't prove it, but the support is going in the direction. Okay, so these ideas are pretty crucial. They're very, very important. So I just wanted to get that across first. So let's go back to our slides. We defined all these things the last time, so I won't dwell on this. See, I'll just say the null hypothesis is the guessing hypothesis. If you are given two options on a true-false test, then in the long run you get half right. It's a long-run statement. This is blue. This is the alternative. No, you're smart. So the alternative is an opposing statement to the null. The null says that you are guessing. The alternative says that you're smart. All right. Okay. So we have this, and let's move on. And then we define the p-value. We just talked about this. A small p-value indicates evidence against the null. Why? Because if your p-value is small, are you likely to get that kind of score when you guess? And the answer should be, if your p-value is small, what does it indicate? Are there many cases where you get a score as good as that? The answer is no. That's why it's small. And if you don't get that kind of score a lot when you guess, that's evidence against guessing. It's actually very logical if you really think about it systematically. Then the opposite is true if your p-value is large. If your p-value is large, it means that no, this kind of thing happens quite a lot when you guess. And so we have no evidence for the alternative. There's no evidence that you're smart. It's plausible that you're guessing. If you get 52% on a true-false test, is that evidence that you're not guessing? No, it isn't. Because you get scores like that all the time when you guess on a true-false test. That's what's going on. And then we have the strength evaluations and things like that. Okay. See, the smaller the p-value gets, the stronger the evidence is against the null hypothesis. Not proving anything, not disproving anything, but it's an evidence game. So today we are going to continue with this one. I will need your audience participation because we're going to do a lot of these things on spreadsheet. Then we'll have a sheet for you to work on, but we'll learn first, okay? So far we have always made claims about the long-run parameter pi. We then looked at how strongly our observed statistics supported the claim. We used the p-value to assess strength. We just talked about this. There is an alternative to using the p-value as a strength evaluator. So we'll get there now, all right? So far, we've been talking about the purple fraction. So let's talk about free throws again. Let's say I do basketball free throws, 100 of them, and I made 78. Let's just say. It's not true, right? But, okay. So what's the symbol for this? What is 78 out of 100? This is very good, right? P hat. First of all, it's a proportion. It has to be P. Why is it not pi? Can anyone tell me why is this not pi? Why? Can you give me a simple reason? Pi is a proportion, but why is this not pi? It's not long run, yes. When I hear answers like that, it makes me so happy. Despite the terrible conditions outside, it makes getting to work. Well, I thought I might not even make it, honestly. The car was not responding in any way. And we only had 2 days of school. Can you imagine how bad the roads must have been with that the school? Hope never closes, let me tell you. Right? So the fact that they closed means it must have been okay. So anyway, so we use the symbol p hat, right? It's not pi because it's not long run. It is not long run. Because how do you know it's not long run? Can I do more than 100 free throws? Of course. The fact that I'm stopping at 100 means it's not long run. See? So we use the symbol p hat for that. Let's say we want to test this thing now. I purposely picked this because I want to show you the status quo value of pi doesn't always have to be 0.5. I think you all know that. I made it a point to give you homework where pi can be other things. If you talk to your friends in other sections, which I think some of you do, you'll find that a predominant number of their examples always have pi is 0.5. And I have found over the years that that does students a disservice. They think that pi must always be 0.5. No, it depends on the situation. If you're talking about true false test, yes. See? I'm talking about basketball here. Where do I get this number from? Who knows? Maybe it's the NBA free throw rate. Maybe it's my friend's free throw rate. Maybe it's what my free throw rate was 5 years ago. All right. So this number actually is set by you or what you want to test. If this is status quo, see, I want to test whether I'm doing better now. This is my current free throw rate, not my historical one. This number comes from a comparison that you want to make for some reason. In other words, can I test pi is 0.7 if I wanted to? Yes, I could. I can test anything. Can I test pi is 0.5 if I wanted to? I could. This is in line with the homework problems where I say, the proportion of college students 50 years ago who slept in was what? See, so you want to compare whether current rates are the same as what they were or what they are in another school or whatever. So that number comes from somewhere, and we don't bother about why they're testing that. We just happen to be interested in testing that. So pi is your long run free throw rate now, not historical, right? You have to distinguish. Pi is your current long run free throw rate. I just want to see if there's evidence that I'm doing better now in the long run. See, that's why statistics is important. Sometimes we lose sight of this, we say things like, but I got 78% on my recent try. Aren't I doing better than 75? Yes, but for that sample. The moral of the story is statistics is, in the long run, is there evidence that I have done better? It's very key, I hope you understand this. Let's say my historical rate or my friend's rate or the NBA rate is 75%. I want to know whether in the long run I'm doing better now. You can't just do 100 and say, oh, look, it's 78. I'm doing better. Yeah, that's based on 100. What if I get another? What if I ask you to do another 100? And that's the purpose of simulation. You get the computer to say, okay, let's see what happens whenever you say your free throw rate is 75%. Most of the time when you simulate that way, you will get things with 75% free throw roughly around. Sometimes you get the odd one where you do very badly or very well. And the whole point of statistics is, how rarely do you get scores at 78% if in reality your free throw rate hasn't changed? All right, that's what's going on. So don't worry if it takes a little bit more time to process this, it will get better, all right? We can also test other hypotheses as well for different values of pi. You can write some down if you want, but don't confuse yourself if you don't want to. But you could test pi is 0.7, 0.6, 0.5, 0.2, anything, right? So what is a simulation-based p-value? So this is where we are going to ask you, if you can, to contribute to this. Now, here's our scratch pad. I will label this here this way. Okay. So free throws case where p hat is 78 out of 100. Can I see a screenshot, someone? Now, there's quite a few screenshots we want to do today. So if you could cooperate with me and just paste it here, it'll be good. Then the class can move along. If we wait too much, then, okay, so here's what I want. Okay, something like this. I want to see everything from the top left corner all the way, and then make a few things. Make sure you're in proportion mode. Make sure your red line is in the system, and show me what you put in the count box and things like that. This is good revision for you. I mean, I can do it, but I want you to do it. So I want you to do it for this free throw situation. We are trying to test whether there is, what are we trying to test? We are trying to test whether there is evidence that my free throw rate now is actually better than what it was before or whatever, right? I got 78 out of 100. I'm testing whether there's evidence that my free throw rate now is better than 75%. So can someone fill in the correct things into the applet and then paste your screenshot? Just make sure you're in proportion mode, and draw that red line, okay? Then I'm going to ask you to do something. So paste first, then I'll ask you to do something. So you erase it and put it back, all right? Paste it first, then I'll ask you to do something additional and then put it back, all right? So can I see? So this is the free throw case where my p hat was 78 out of 100, right? I want to test if HO, wow, HO pi is 0.75 versus HA pi is more than 0.75. Okay. And if you could, try to shrink your graphic so that it doesn't take up so much, because we do have quite a few screenshots we're going to get through today, right? Because today's class, as with all intro, all the beginning classes are very important. Today's class is as well. So thank you. Let's have a look. And hold on to it. Don't throw away your screenshot, because I'm going to actually ask you to erase it and repaste after doing one thing. By the way, this is correct. Let me tell you why. Why is this 100? Aren't I trying to reflect my study? I did 100 free throws, right? Why is this 0.75? That's status quo. I'm trying to test whether there's evidence that I'm doing better than 0.75 now. You need to have a starting value to simulate. This is the blue number. Do you see the red number? Do you see the 0.78? That's in red. Can anyone tell me what is the p-value? Can you give me a number from the screenshot? I will type it here. What is the p-value? Anyone? Do you see it? It's such an important number. It gets repeated quite a lot. I know it's not colored purple. What is the p-value? Anyone see it? You can just shout it out if you can see it. Then I'll type it down. What is it? 0.273. See? I know it's hard, right? I know there are so many numbers on the screen, but it's 0.273. Okay? So if someone could type it in, I'll type it in. But you know what? Can someone highlight 0.273 in purple? Can someone do that? All right? I don't want this culture of putting it in red. I know the applet puts it in red. It's very confusing. I figured out that's why students get very confused. They think this is the observed proportion and all that. There are so many things that could go wrong teaching this. I do understand. It's confusing. But 0.273 is the answer. Good. Now, is this pretty big? According to our scale, is there any evidence that I'm doing better? See, there's no evidence. This is a huge p-value. It means a one-off 78% score is nothing to get too happy about. It does happen. When you have a free throw rate that's really 75% and you do 100 tries, it is quite possible to get 78%. See? Okay, so that's why statistics is useful in that sense. It helps us evaluate the strength of evidence. So whoever pasted this, I'll ask you to do one more thing. Can you check this box? See, you have the proportion mode, which you are. When you are in proportion mode, check this box. Can you repaste the screenshot? Right? Whoever did this, I want to retain this simulation. Can you check that box, then repaste? There is one number I want to show you. All right. Thank you. Do you see, that was very fast. Do you see SD equals 0.043? Okay, this number is very important. And I'm going to type it here. We will record the SD here. This SD is what? You know SDs are measures of spread. The SD is the SD of the null distribution. What is the null distribution? It is that these dots, it is the spread of these dots. This number is the fourth, and dare I say, final number we're going to introduce. So I'm going to give you another color. Right? This is not a proportion. This is important as well. I'm going to color this green. All right. This is the last one. There are no other numbers I'm going to pull out of my pocket and show you. Okay, that's it. All right. And this is important because this introduces what I'm trying to talk about today. Right. Now, so can you record down in your slides the answer? What is the simulation-based p-value? 0.2743 or thereabouts. All right. The simulation-based p-value is 0.274. Now say, instead of observing 78 out of 100, let's say I observed 156 out of 200. Now I've chosen this example for a reason. Do you see, first of all, that this is based off 200 throws. Second of all, do you see that both of these are 0.78? In your gut, can I ask you, which result, although they're the same result, they're both 78%, which result is more spectacular? The second one, isn't it harder to get a 78% free throw rate when you do 200 tries versus 100? It is. So, do you think the p-value is going to drop or go up if we do this? We're going to do the simulation. I'm going to ask you to do that same thing for this new scenario. You have to re-simulate because sample size has changed. Do you think the p-value is going to go, is it going to be going up or down? Which one? It's going to go down. Very good. Why? It's less likely. You are less likely to do as, see? And is the evidence against the null going to increase? Yes. All right. So let's have you do the same exact thing now, but I'm going to do it this way. I'm still testing the same thing. I'm going to copy all these and I'm just ask you to re-simulate. Make sure you check that summary statistics box and paste it right up top here, right? Can you just paste it here? Right. In other words, I want you to do the same thing that was done in the screenshot, but now based off 156 out of 200, which of course, is still 0.78. Right? The whole point is to show you that the evidence is stronger now, as you have correctly surmised. All right. So can I see? We'll correct these things after the screenshot gets pasted. Make sure you have that number that I put in green so you can compare. All right. Thank you. Let's have a look. Perfect. This is very good, you know. All right. Let's have a look. Y 0.75. Am I testing the same thing? Yes. I didn't change it. Don't change something midway and try to compare. This literally apples and orange. Well, not literally, but that's where the same comes from. So see, 0.75. But now I did 200 throws. Why is this number still red at 0.78? Is that still my sample rate? Yes. Why is it centered at 0.75? Because I told it to do that. But can you correct now? There are two things wrong here. Can you correct the p-value and correct the SD? Keep the colors, okay? Keep the colors. What's the p-value now? And what's the SD of the null distribution now, based off this screenshot? And by the way, exams will be like this, where it's based off screenshots. You don't actually use applets on the exam, all right? I give you screenshots like this. So, where's the correct SD? It's not 0043 anymore. What is it? Yeah, 0.031. And the p, you're right, the p-value is a fraction s or more extreme, and it's now 0.188. Do you see that? So is what you say come true? Did the p-value go down? Yes. In other words, as your p-value goes down, your evidence against the null goes up. There is more evidence now to say that you might be doing better than 75%. It's still big. P-value is still big. Okay, but it's gone up. The evidence has strengthened, the p-value has went down. All right. And one more thing I want to point out, even by eye, can you see that which distribution is more spread out? Is it this distribution or is it this one? This is more packed together, right? And what do we know about the SD? SD measures spread. The spread is lower now. The distribution is less variable. Now, does that make sense? Aren't larger samples less variable? Yes, there's much more variability. I mean, if I did 4 free throws, then there'll be a huge variability from try to try. But I'm doing 200 versus 100, it's more stable. And so the variability has gone down and you have correctly changed these numbers. Very good. So let's go back to our slide. What is a simulation-based p-value? You can put 0.188 and you can say, look at Scratchpad or whatever, something like that. Which null distribution has higher variability? The one where the sample size was bigger or smaller? Which simulated distribution had a bigger spread, more variability? The one with the smaller sample size or the larger sample size? The one with the smaller sample size. Very good. Higher variability is, I didn't answer this on the slide. You have to write it down. The null distribution has higher variability when the sample size is smaller. Now you can learn it any way you want. If you like to learn it as which null distribution has lower variability or smaller spread, the one with the bigger sample size, just learn one. All right. So I'm going to introduce now something new. This is the alternative measure of strength of evidence. That's not the p-value, but it's equivalent. It's something I call SIMZ, and it will only make sense after this class how you can do your homework. Your class got put off by 2 days, so don't worry. I think I've already extended whatever. So SIMZ is this one. I know there's a lot of words. I will use colors. That's why I like the whole color thing I've been doing. I'm going to copy this. And I'm going to ask you to tell me what colors you should use. SIMZ is a number, of course. Okay. I'm going to paste this on Scratchpad, and you tell me, based on what you... well, what got pasted? Let's see. Oh, yeah, it's here, actually. So let me... okay. Let me try to do this and see. This is the numerator. So I'm going to put it in the parentheses, and you divide by the standard deviation of the null distribution. Okay. Can anyone do this? And if you can do this correctly, I will be overjoyed. There are basically 3 numbers here. Can you highlight with the correct colors what they should be? There's an observed statistic. There is what the null hypothesis says the parameter is. And then there's a standard deviation of the simulated null distribution. Lots of words. But can you tell me which color you should highlight which number? There are 3 numbers. This is a number. This is a number. And of course, the standard deviation is a number. What colors should you use? Maybe start with the simplest one. I've just introduced the standard deviation. What color do we use? We use green. Very good. Let me ask you, first of all, let's eliminate. Do you think the color purple, which is a movie, by the way, do you think the color purple makes sense in this formula? Does it belong in this formula? It doesn't. There's no mention of the p-value. And so there's no purple, which means you're left with 2 other options, right? Which one goes where? It's very telling. If you can color it correctly, then you understand, you see. It's the observed statistic minus what the null hypothesized value is. What color goes where? The observed statistic needs a color, yes. Anyone know what it is? Before it gets colored, anyone want to try? Does everyone agree with this answer? Is the observed statistic blue? Which one's blue? Blue needs to be there. Which one is blue? You can make corrections if you think that, if you don't think that that's correct, you can make a correction. What the null hypothesis says the parameter is the one that's blue. Because the word parameter is there. That's the pi value in the null. The observed statistic is always, always, always red. Because you see it. It's observed. The parameter you don't actually know, you hypothesize. Okay? Does this help you? I hope so. Right? That's it. Put these 3 numbers in and then calculate SIMZ. So let's go back to our slides. So there are guidelines for SIMZ values. So I'll go through this first. Before we do any more math, I'm going to tell you, this is an equivalent strength of evidence chart with the p-value chart. You notice little to none, moderate, strong, very strong. If you compare to the p-value, you see an equivalent chart there. But do you see something different? SIMZ, the larger it gets in size, we don't care about the sign, The larger SIMZ gets absolutely the size, the stronger the evidence is to reject the null. Sometimes that makes SIMZ a bit more intuitive. Does that make sense to you? If it doesn't, learn it as a rule first. We will see why this makes sense. These guidelines are, as your Z value that you calculate gets bigger, the evidence against the null gets stronger. This is the different direction happens for the p-value. The p-value, as the p-value gets smaller, the evidence against the null gets bigger. So these two slides you need to compare and contrast. They are telling you the same thing, but in different directions. So I like to give this illustration, and you all know what a seesaw is? Okay, do you use that word in America? I found out here they call it a teeter totter, something very difficult like that. Why do that? Seesaw. Okay, so okay, why am I talking about seesaw? A seesaw, teeter totter is very close to another word, teetotaler, a person who takes no alcohol. But anyway, so the seesaw, why am I talking about seesaw? Because if you sit on one side of the seesaw, if you are the p-value, when the p-value goes down, SIMZ goes up. They go in opposite directions, but they're telling you the same thing. Did you see that? As your p-value goes down, your strength of evidence goes up, SIMZ goes up. As your SIMZ goes smaller, p-value goes up. So think of a seesaw when you learn these things. They tell you the same thing. The strength of evidence evaluation is the same, but they go in different directions. Okay. So calculate SIMZ for these two cases. Can I ask you to do these things on Scratchpad? So we see it's not going to take long because we have already primed everything up. Let's do it this way first. Let's go to this case. Based off this, all the information here. Oh, I think I know what I'll do. I'll bring this up one step and I'll bring this here. Oh, it doesn't like that. Okay. Well, let's shrink this picture then so that it doesn't. Okay. Can we calculate SIMZ? SIMZ, I'll start you off. Something minus something over something. Three numbers. Can you look at this situation? Look at the numbers here. Look at what we tested. Look at our red number. Can you tell me what are the three numbers? SIMZ is something minus something over something. Three numbers. Red minus blue over green. That's right. The green number is 0043. Good. If you want to help the class, you can color this in green. I think we should actually. So 0.043 is the SD. Good. What's the red number? What's the observed statistic? 0.78. Good. What is the blue number, the hypothesized number? 0.75. That's right. So good, that was fast. So can someone go and actually calculate this? You can use an online calculator or whatever. That would work. So 0.78 is the observed, and 0.75 is the hypothesized. All very important. Good. What is this? How much is this? It's pretty small. Okay, thank you. So have a look at this. Let's go back to our scale. 0.69. Where are we? 0.69 is in this zone. So is there any evidence against the null hypothesis? None at all. Was the p-value large? Are they consistent? Are they telling you the same thing? Yes. So the seesaw is in effect. So Z small, p-value big. See? But they both tell you there's little or no evidence to reject the null. Good. Let's do this quickly for another one. Can you calculate SIMZ for the second case? Let's say I did more free throws, 200 of them. Can you just change actually one thing? Because in this second free throw situation, did I also see 78%? I did. So this doesn't need to be changed. Am I testing the same thing? I am. Yeah. So the red and blue don't change, you see. That's why SIMZ is a necessary way to understand strength of evidence. The distances from the numerators are the same. 78% is the same. It's the same 78%. the distance from 75% remains the same, but the thing that changed, yes, was the SD. Very good. So can you recalculate this? It's going to go up. It's going to go up a bit bigger. And is that consistent? Do we have a bit more evidence against the null in this situation? We did, because the p-value was slightly smaller here. See? So what is 0.78 minus 0.75 and then over 0.031? What is the new number here? Something a bit bigger. I think it's going to be closer to 0.7 something, if I'm not mistaken. Oh, already? Okay, thank you. So almost one, actually. So did the Z go up a little bit? Yes, it's so the evidence now is stronger against the null. Still in that zone, this kind of SIMZ is still in this not exciting zone, little or no evidence, but it is bigger. And consistently, the p-value was smaller in this situation, as you have rightly pointed out. Very good. All right. So I'm going to shrink this picture a little bit so it doesn't disrupt the flow. Okay. All right. Yes. Oh, it is, but it's just that in this case they were the same. Because I'm trying to compare apples with apples. You basically got 78% when you did 100 versus when you did 200. So the point here is, how do you, in other words, how do you distinguish between two people who both get the same score? And that's why I gave you, I don't know whether you remember, there was a worksheet last week. No, it seems so long. Not last, well, yeah, last week. Where we talked about taking a multiple choice test with 10 questions versus 100 questions. Isn't it somehow your gut tells you it's harder to get 78% on a test when there are more questions? See? That's exact. That is why it is not enough. That is why it is not enough to just look at this distance. I hope you see the logic here. Someone can come along and say, I did 100 free throws, I got 78%. Okay. Someone can say, I did 1,000 free throws, I got 78%. Who's better? Clearly, the one who did 1,000 free throws and got 78%. So, how do you factor that in? That's where this green number comes in. That's very important. It is not enough to just look at the distance. Yes, it's a starting point. All right. And this is like, thank you. This has been very good. So, let's finish our slides and go on to some other things I want to talk about today. So, when do you have stronger evidence against the null hypothesis? When your p hat is the one that came from the larger sample size, which makes sense. It's harder to get this kind of score with more tries. It's harder. So let's look at factors which affect the strength of evidence. Okay, so as just has been pointed out, one factor which can affect the strength of evidence is how far away the observed statistic is and the value claimed in the null hypothesis. In other words, the red number versus the blue number. The distance between red and blue. Which is a metaphor for something right now. Right? The distance between red and blue politically is very far now. Right? But anyway, so the distance between red, observed, and blue, hypothesized. The larger that distance gets, is the evidence stronger? If you are getting scores like 90% versus 75%, is that very distant? Yes. The larger this distance gets, the stronger your evidence against the null. Of course, you say something. You say you're guessing on a true-false test. That's 50%. But you come and report to me that your score is 97%. That's very far away. So the farther the distance is from the observed to the hypothesized, the stronger the evidence. That's simple. Can anyone tell me what they think factor number 2 is? What do you think factor 2 is? This is just talking about distance. Anyone have any guesses? Before I tell you the answer, what do you think is the second factor that affects strength of evidence? We've talked about distance. Have I just been talking about something else that affects strength of evidence? Sorry, what? That's okay. I think I heard the right answer. Anyone have any ideas at all? What is the second thing that can affect strength of evidence? Distance is one. The other one would be? Because we were just saying that distance alone is not enough. So what is the other thing? Distance is definitely one factor. We've talked about it. What's the second factor? Anyone want to try? Yes. The sample size, which translates to what? Yeah, right. The sample size, which translates to that SD thing and all that. All right, we just talked. Now, the third one, I don't expect you to know. I want you to copy first because you don't even know what I'm talking about. Whether the alternative is one or two-sided, you'll get that, right, in our example. That's the third thing we haven't talked about yet. 1 and 2 we have discussed. Do you see that 1 and 2 are the numerator and denominator of the SIMZ? The numerator of SIMZ was the distance between red and blue. That's factor 1. The green number is controlled by the sample size. That's factor 2. Red, blue, top. Green, bottom. Factor 1, factor 2. Factor 3 is not given a color, it's a thing, right? So we will talk about that when we talk about, okay. So I have generated an example to teach you these 3 factors. Predicting election winners correctly from candidates' faces. So I'll tell you what happened. So in the US, roughly 32 Senate seats go up for election every 2-year cycle. That's how it is. We don't have time to talk about these things, but when I first came to this country, I knew absolutely nothing about US government. Now I know more than I want to know. Right? But anyway, so there are 100 Senate seats, senators anyway. So about a third get up for re-election. So that's where this data set comes from. So what they did in 1 year was, in that particular year, they took all the 32 races. And in this country, for good or for bad, there are points on both sides, there are only 2 major parties. Okay, what am I getting at? So they put the 2 candidates' faces, race number 1, race number 2, race number 3, up to 32. Now here's something interesting that they did. They actually went around to people who are very, very apolitical, who don't care. They don't even know anything. They are the kind that don't even know who the vice president is, that kind of thing. There are people like that. I think there's almost no one who doesn't know who the president is, but you'll be surprised. But okay, so they ask people. They don't know what the candidates stand for. They don't know, and they don't even know what party they're from. They just said based on just their looks alone, based on just what you look, tell me who you think should be senator, just based on your face. All right. Now, so let's say in race number 1, a majority said face A. I will then make the call that I think A is going to win. That means I predict based on people's popular opinion, just based on looks alone. Did you get it? And the scary part is that they got it right 23 times out of 32. This kind of statistic should scare you like crazy because it means that nothing matters anymore. And this is an old data set, and this is a real data set. It's scary. All right, so you don't even know what they stand for. It's just that, I don't like how this person looks. So this method of predicting who's going to win was pretty effective. So what do we want to test? Can you guess? Since there are two candidates per race, what do you think the null hypothesis says? Pi is, there are 2 candidates per race. And so if the method were not effective and it's as good as guessing, pi would be, as usual, what? What proportion would pi be under the null hypothesis? That's right. And that is only true because in this country, there are only 2 candidates viable anyway that are put forward for each race. What do we want to test? We want to see, are we doing better than just guessing? So you see, what is pi? Pi is always a long-run probability of what? Well, some kind of proportion of correctly predicting the Senate race winner based on just the face. In the long run, how well do I do? If there were no advantage to this method, I should get about 50% of the races correct. You see the logic? If there's nothing to this method, then I'll get it right about half the time because there are 2 faces for each race, you see. If there's nothing to this method. But if there's something to this method, then I'll do better than 50%. So calculate SIMZ and report PA. So there's quite a few screenshots I want to get through, and I'm trying to finish this by 1 o'clock to give you enough time to do the sheet. So let's have you participate on Scratchpad, right? Let's copy some things. The scenario here is not free throws, but you'll notice a lot of things can be recycled, and I'm going to do that. I am going to put this here. I'm going to stop using the word recycled if I can. It's not it's repurposed, right? I prefer that word. Okay, so it's not free throws. It's Senate races. And the case where p hat is 23 out of 32. You want to test whether pi is 0.5 versus whether pi is more than 0.5. Can I see a screenshot with everything there, like what you've done? All right. Can I also ask whoever pastes the screenshot, make sure your SD is there. Also, paste it first. I'll tell you to do one more thing. All right. And then paste another thing. Right. Let's do this first. Right. Paste the situation for testing this one. Then we'll correct these two. All right. So now we have a Senate race example. P hat is 23 out of 32 correct. The null hypothesis says pi is 0.5 in the long run. Alternative says pi is more than 0.5. Let's get the p-value and the SD out, right? Let's see the simulation, all right? And then we'll ask you to calculate sims. Okay, I don't want this to be in green here, so I'll put this down here. I'll also ask you to calculate sim-z after we have all this information here. Okay. Thank you. Let's have a look. Is this correct? Yes. So you see, pi is 0.5. Why 32? There are 32 Senate races. And then, why is the observed statistic 7188? That turns out to be 23 out of 32. So if you want to make it clearer to the class, I will put the decimal here. This is, now AI wants to be smart, okay? 7188, right? Can someone put the correct color on these things? That will help. What should the color be for the 23 out of 32 or 0.7188? What should we color these things in? All right. This one should be colored red because that's what you saw. Good. Can someone change the p-value and the SD of the null? Do you see the numbers on the screenshot? That was fast. I think, okay, I think it's 008, right? Do you see that? I think it's 008. I thought I was seeing it wrong. According to the screenshot, it's 008, but thank you. What's the SD? Do you see a 0.09? I hope the color thing is helping. It's even helping me, honestly. It just makes it a little bit clearer. Really, it does. I'm so happy that I thought of doing this. Okay, now here's the second thing I want the one who pasted this to do. Can you paste with something extra, which I've never asked you to do? We'll paste it bottom and then we'll call it out later. I want to use this one because I want to do a direct comparison later. Can you check the two-sided box and paste screenshot here? Don't erase this one. Add this two-sided, check it, and paste again. All right. Then we'll revisit this in a minute. All right. Also, all right. Thank you. We'll get back to this. Not yet. Right. We'll get back to this one. Thank you. That's perfect. Okay. So what's SimZ? Can we do this quickly? Something minus something over something. And let's have someone calculate the actual number as well. All right. If you want to use colors, you can, but I think y'all are getting able to do it without already. Observe, yes. Minus hypothesize over ST. Very good. And what's the hypothesized value of pi? Thank you. That was fast. Okay. So I'll quickly. Thank you. All right. Is this a large z value? Yes. This is evidence. So because getting it correct 70 something % of the time is scary good. It's really good. It's quite far away from 50%. That's excellent. So now let's go back to our slides. I think you can fill in all these. Calculate SimC report p-value. So you can write these things down in your slide. All right. Okay, so factor number one, just to prove a point, let's say we want to talk about the distance between the observed stat and the hypothesized parameter value. Let's say we actually saw p hat is 25 out of 32. Now, I know I'm depending on the person that did this, and I'm sorry to depend on you so much, but you really have a very good screenshot. Can I ask you to do another thing? I'm going to talk about what actually happens if, so save that. Do you know you don't have to resimulate? I didn't change anything, but now let's say I'm faking it, but let's say I got 25 out of 32. Can we make some corrections? You don't have to resimulate. It's still based off 32, but can you repaste your screenshot with the red line now in the new corrected position? Now you saw 25. Thank you. 25 out of 32 that has to be corrected. It's now 0.78 or whatever that is. It's even better now. It's even better. It's more spectacular. The moral of the story is this is even farther away from 0.5 than the previous result. So should the evidence against the null be stronger? Yes. The distance argument is if what you see is more extreme, the evidence is getting stronger and stronger. Thank you very much. So here's the, see, oh, I'm sorry. Can you take away the two-sided box and repaste? Okay, I forgot to tell you to switch that off. But this is correct. Just remove the two-sided and repaste. I'll just erase this, okay? See? Thank you. So you see, okay, so let's report a few things. Has the p-value gone down? From 0.008, it is now, do you see it? The purple number has gone down to what? It's not 008, but, and what's, ST is the same, because you didn't resimulate, but the purple number is not this anymore. The purple number is 002, it's gone down. And can you make some corrections to see, oh, okay, this has been corrected. 7813 is the new observed. 0.5 is still 0.5, as this, okay, this number is wrong now. What is it now? All right. 0.7813 minus 0.5 over 0.09. You would think in 2025 that AI would be smart enough to calculate this, but it's not. It's still not that good, which, you know, it's not a bad thing. You don't want things to be so smart, honestly. So you still need to copy this and go into an online calculator or something like that. So what is it? Thank you. So see, is it bigger now? So the p-value go down, the z go up? Yes. Is the strength of evidence against the null increasing? Of course, because you did better than what you did. Good. So you can go fill in the other parts of the slide. We still want to test the same things. And so you can actually say see previous slide. There's nothing has changed. You're testing the same thing. The situation has not changed. We are not testing anything new. Calculate SIMZ and report p-value. We can do that. It's on Scratchpad already. So you know what we're going to do naturally. Sample size is the next thing. Sample size is the next thing we're going to talk about. Now say we actually had 230 out of 320. This is a super hypothetical. It's kind of fake, honestly. This means America has 320 Senate seats up for re-election. And you can see clearly, I picked 230 out of 320 because that gives you the same thing as 23 out of 32. See? So we still want to test blah, blah, blah. This one, this one, this one. Everything is the same. Testing the same thing. But now it's based off 320 Senate races or whatever. Or maybe just, let's go away from the Senate. Maybe we just change it to a House. House seats is, House, every seat goes up for re-election every 2 years, I believe. I think I'm right. So, and the House seats are about 500 something. So let's just say there are 320 House seats, and you get it right 230 times, something like that. See? So let's have you do this as well. So to make it more realistic, I'm not going to call it Senate race anymore. I'm going to say House races, okay? Let's say House. So CP hat is not 25, 230 out of 320, which is how much? Let's see. Oh, AI is not helping me. Okay. This was, what was this? I can't remember now. This was 7-1 something. Thank you. Yes, that's right. We are still testing the same thing. Can you report these three things and show me your screenshot? All right. We'll change all these things. All right. Can you anticipate what's going to happen to the p-values? Is this evidence even super strong, right? Getting it correct 230 times is a very, very spectacular thing. All right. What is the new p-value? Do you see it? I do. The new p-value is, that's right, 0. That's right. Good. Yeah, I was gonna do that. Very good. 0. Effectively, you cannot get so good on a true-false test where you guess. Not that you cannot. If you do it enough times in the simulation, you will produce it one eventually. The SD of the null now is, see, can you see just by eye alone that this is a much more bunched up standard deviation? The null distribution here is much, much more focused. There's less variability in larger sample sizes. And SD is a measure of variability. So we have that. Very good. Compared, you see, even visually, you can see this is very spread out. This one is bunched up. All right, good. So 0 is the p-value. SD is this one. See, distances, I think this is going to be humongous. I'm not sure how big though. 7, 8, I don't, it's something quite big. What is this number? See, 7 something. Our scale just says anything more than 3, and this is 7. So massive, massive evidence against the guessing hypothesis. There is really something to this method because it has been proven to get it right in 72% of the cases when you did it 320 house races. You know, that kind of idea. So that's what's going on. Very good. So the last and remaining factor is whether the alternative is two-sided or one-sided. Okay. So let me talk a little bit about this. And what I will do now is I will take that picture that was originally down there. You know what? Although we learned it in a different order, I will put it here together where I asked you to post it together so that we can do an immediate comparison so that they are both side by side. I want to show you what's same about them and what's not the same. Okay, let me paste this here. See, whether an alternative is one or two-sided, first of all, I want to show you the physical representation of that on the graph. You can see that all the tests you have done so far are clearly one-sided. You only look at one side. A two-sided test looks at, surprise, surprise, two sides. And what do I mean by two sides? How mechanically do we do it? Now pay attention. When you click the two-sided box, what happens is your original observed statistic is 7188, right? You travel from here to the blue box, the middle, the blue, red to blue. Then you take a mirror and you travel the same distance to the other side and draw another line. I'll say this again. You didn't see this. You did not see this. You saw this. Travel from here to the middle, the blue, and then move the same distance to the left and draw another line. So it's a symmetric thing going on, like a mirror image. And you count the places on both ends. There were, I think this is left, this is right. There are 8 cases here, and there are 7 cases on the left side. So the 7 plus 8 means there are actually 7 dots here. You can't see them. There are 7 dots here, and there are 8 dots here. Together, you add it up. This is your p-value. I know this is new. This purple number is still the p-value, but it is based off cases now on both sides. Now, why is this called a two-sided test? I mean, obviously, it's because you go on 2 sides. But basically, the logic of a two-sided test is this. So if we go back to our slides, I'll tell you what it means, okay? See, notice the only thing that changes in a two-sided test is the alternative is two-sided. When you say pi could be not equal to half, what do you say? If I say something is not half, there's only 2 possible scenarios. It's either more than half or less than half. Do you agree? Okay. This person is not 25 years old. Well, it means it's either more than 25 or less than 25. That's the logic. So that's exactly what's going on. So two-sided test is it could be more than half, it could be less than half. And that's the rationale for going to both sides of the null distribution. Now you may think, what is the practical reason for testing this? This means, actually, I don't know whether this method is effective or not. Maybe picking who looks better is going to work against you. I mean, could that happen? Could we live in a parallel universe where the people that don't look good actually are the ones that people would actually choose for Senate? So in other words, they don't base it on looks anymore. So your method is wrong. So it's like, what I mean is this: you ask people, okay, who do you think is going to win? And then you go with, okay, majority said A or something like that. I go with it. But in reality, it didn't happen that way. It could happen. Whenever you do a statistical test, the ethical thing to do actually is to always do a two-sided alternative. So you might have arguments with your professors next time from other departments where you do research with them. If they do a lot of one-sided tests, you better tell them, no, that's not what I learned. If you dare, okay, you should always do a two-sided alternative because it's more ethical. You don't know if what you're studying could go either way. Why is it actually safer to do a two-sided test? Did you see your p-value goes up when you do a two-sided? It goes up because you're not considering cases on both sides. The fact that you're considering cases on both sides is going to raise your p-value. You know that when you raise your p-value, your strength of evidence goes down. So you may think, why would I want to do that? Don't I want my strength of evidence to be high? Yes. But you don't want it to be high based off an unethical practice. In other words, you're going to need to show me evidence that is so strong that when I push out to the two extremes on both sides, I still get a small p-value. That's the logic of what's going on. Let it slowly sink in. If you don't understand what I just said, it's okay. You just need to understand now that when you do a two-sided test, automatically your p-value is going to go up to roughly twice because you're considering cases on both ends. Your p-value is going to get bigger. And is that true on Scratchpad as well? Look at the p-value here. See, this is 0.015 versus alone one side 0.008. Geometrically, we know that has to happen. When you consider cases on one side, you're going to get a certain fraction. Going to the other side and drawing a line and calculating this side, it's just going to add to it, that's all. So the p-value goes up when you switch from a one-sided alternative to a two-sided alternative. Okay, we have covered a lot of ground and you all have done excellently, really good. So I think, let me finish this. Is there anything else to do on the slide? Report the p-value. Okay, yes. So just a few conclusions and then we will give you the worksheet and then we're out of here. The closer the observed statistic is to the null value, in other words, the closer the red is to the blue. Can you finish the sentence? The stronger or the weaker the evidence against the null? The closer red gets to blue, the stronger the evidence against the null or the weaker? What do you think? The closer what you see is to what you say, the stronger or the weaker the evidence against the null hypothesis. If what you see is really close to what you say in the null, is that strong evidence or weak evidence against the null hypothesis? Weak. Very good. The closer the statistic that you observe, the red, to the blue, the weaker the evidence. Again, you don't like this phrasing, you can learn it in the opposite way. You can say the larger or the more distant the observed statistic is from the null hypothesized value, the stronger the evidence. You can learn it positively as well. It's up to you. Can you finish the sentence? The larger the sample size, if your sample size is big, what happens to your strength of evidence? Stronger, not weaker. Because if you have a larger sample size, is that kind of thing harder to, yes, harder to get. It is harder to do well with a larger sample size. And so the evidence gets stronger. Very good. And a test with a two-sided alternative will have weaker or stronger evidence against the null compared to a one-sided alternative. We have just discussed this. When you go from a one-sided to a two-sided test, the strength of evidence immediately will weaken or strengthen. If you change from a one-sided test to a two-sided test, what happens to your strength of evidence? Right? From considering just one set of cases, now you go to two sides like that, your p-value goes up, so your strength of evidence will go down. Changing to a two-sided alternative will have weaker evidence against the null hypothesis. All right. These are the very important conclusions that I want to get to today. And I will now give out this worksheet. There's only 2 questions on it. I want to do this. I want you to do this, and then we will try to discuss 1, 2, 3, 4 pages. Okay. This should not take you that long. Maybe just 5 minutes. Then we'll discuss, and then we'll go. That's it. All right. So give it a try. I will put up the color version. I know it's very ugly, this one. I will put up the color version on the screen so you can see it. Where is it? Yeah, it's here. Okay. Okay, see, okay, if this helps you. Here's the colorized version.
No, okay.
Just make sure your group's names are on the sheet of paper and just hand it in at the end of class. Now, if you are happy with what you have, could I have someone type your answers on Sketchpad? We'll discuss. Now, don't worry if you get it wrong. Don't change what you have on your sheet. I told you your sheets are graded by completion. I want to know what you know, but we need to discuss what the right answers are. So don't change your answers if they are not exactly correct. That's okay. All right. Okay, so can I have some answers here? First of all, the parameter is always given a Greek symbol. Very good. It's pi. What is the status quo value of the parameter? We know it's 0.65. Well, my eyesight is so. What is the? Yeah, you're right. It's 0.65. I can almost not see. Do you see the pi here? 0.65. Sample size is 80. Good. What is the symbol for the observed statistic and its value? The symbol is p hat. Good, but no one has filled in the value. What is the observed statistic here? Is it clear from the picture? You know what? I'm going to ask you guys. Can you color in? Can you color in the correct colors for those numbers? Let's do that. What color should pi be? Hmm. Can you show me your work for SimZ? Something minus something over something. Pi should always be blue. Pie should always be blue. Actually, I wouldn't eat a blue pie. Although a blueberry pie. Okay. So what is the status quo value? Status quo value is always colored what? Parameter value is always colored blue. That's right. That's also blue. Sample size, we don't give a color, but if you, because I don't want to confuse the class, but so there's no color for the sample size. This one's blue. Oh, what's p hat? No one's told me what p hat is yet. And what color should this be? All right. The observed statistic according to the screenshot is yes. Actually, you can take the answer from there. The observed stat is 0.725. Very good. And the green number is the SD. Very good. Report the C value. Perfect. Right? Every answer is correct. That's very, very good. So I will take this and put this here. All right. So you know what I'm going to ask you to do? And then we'll go off after this. Well, we've already done everything here. That's great. Pi, yes. We know that pi should be colored. Is it still based off 0.65? Yes. Sample size has gone up by 10. It is now 800. Then it's still 0.725. That's right. But your SD has gone down to 1.6, 4.6. You all are almost doing it too fast for me. Report the p-value 0. Perfect. Thank you. Have a good weekend, all right? That's it.